So very good afternoon to you all. So this will be the last lecture in this series. So today we will talk about basic image processing, and we will do some classification on the images using some machine learning algorithms. So what is image processing? So anyway, we have discussed basics of image processing earlier also. Just so what is image processing? So image processing is a method to perform some operations on an image in order to get an enhanced image or extract some useful information from it. So anyway, any image is represented as numbers in the computer's memory. So applying some operations on the image, maybe like rotating the image or applying some algebraic operations or equation on the image. In order, so the purpose may be either we want to visualize, improve the visualization of the image for enhanced visualization, or we want to extract some information, like we want to extract the water bodies from the image, or some features like road, buildings, etc. So that is image processing. Or suppose if you want to extract the edges from the images, so some kind of operation, so that we can enhance image or extract some information from here. Like here you can see that this is an grayscale image, maybe this 16-bit. So this is some part of Uttarakhand. So this is the, suppose this image is represented at 16-bit. So the grayscale levels range from 0 to 65535. So this is after some processing. Like we can say that after dropping the changing the least significant bit of the image from 1 to 0. So this is slightly different because now the grayscale levels had slightly changed. So you can see the difference between these images. Actually, the differences are not quite visible because we have here the only just the last bit LSB of the pixel intensity has been changed from 1 to 0, and here now this is actually, this is like the initially the grayscale, this was a 16-bit image. So now this is after converting the 16-bit to 8 bits. So grayscale level has been reduced 1/8. So here you can see the change in the image. So this is also an image processing. So image processing can start like a simple image processing could be a simple operation like addition, or like here we have truncated the last bit, or now we have rescaled the image, or it could be something quite complex operation like image segmentation, where we identify like each pixel whether that is a particular some object is there in that image or not, like image segmentation. Or suppose we can create some maps from the images. So this is basic image processing. So these are the fundamentals. So this is the basic image processing. So now let us see for the actually basic image processing operation. Anyway, we have learned how do we read raster data. So after we read, once we read a raster data, we get a two-dimensional or three-dimensional matrices, 2D or 3D arrays. Now anyway, because that those are numpy arrays, so we very easily we can apply any operation on that numpy array. So actually on these things, there actually for this basic image processing, we will use a Python library or a library called OpenCV. So actually OpenCV is a C++ library for image processing. Though Python bindings for this library are available, so I will be using the OpenCV Python bindings for some basic image analysis. Anyway, those whatever things I am doing here, most of the things can be done with JDAL, with the basic NumPy arrays only. But actually, if you want to do some advanced image processing, so then for that we can use OpenCV. So anyway, this is an ordinary statement like we have been using it in previous case also. So I am just importing the required libraries. Then os.chdir. Now my data is available in D drive Haridwar multi. So in that folder my data is available. So I am just changing my working directory to this directory. And here I have a multi-band TIFF image of Haridwar region. Now similar thing, now we are just opening the file for reading. This is a previous time jidal.open, or directly one. So then we are ts.read as array. Now the image intensity values, we are reading the image intensity values and assigning to another variable called image. So image will be a uh, two-dimensional array. So now let us inspect the shape of this image array. So the shape of image array is 4 cross 115, 4 cross 115 cross 1151. So there are four bands in the images. So every band has 1151 cross 1151 pixels. Now actually OpenCV or any other library, actually they need data in a different shape. So instead of 4 cross 1151 cross 1151, actually they need data in, actually they can work either grayscale image or RGB image. So now we will take only for processing using OpenCV, we will just take three bands of this image, like first, second, and third band from the image, and we will reshape the image to a different shape. So actually, instead of now we will take it as 3 cross 1151 cross 1151, and we are reshaping it such that the channel value comes at the last, like RG or B comes at last. So we will reshape it to the shape of 1151 cross 1151 cross 3. So now if I see the shape of this image, so here actually what I have done, I have actually this my original image is a 4 band image. So I have just taken out 3 bands from that image, like first, second, and third band, and just reshaped that to a 3D array to another shape. Instead of 4 cross 1151 cross 1151, I have reshaped it to 1151 cross 1151 cross 3. Now I have like every with every pixel I have assigned that value of that pixel in red, green, and blue. Suppose if I see this data, now see the data is like this. So this is the pixel one's band 1, band 2, band 3. That's like second pixel, band 1, band 2, band 3. So this way now we have rearranged our data. So now first operation we will do in the image, like rescaling the image. Rescaling the image means we just are changing the intensities of every pixel. Like suppose if you want to double, like so we want to multiply the every pixel's value by 2. So that is a quite simple operation, because image is now as image underscore REC. This is RES. This is an this is a three-dimensional array. Now suppose just if you want to scale every pixel's value by 2 or 3, so you can just image rescaled is equal to whatever our image reshaped cross 2. So this will just rescale the image. So now let us visualize both images together. So here we can see that this is our this is our original image, and this is the rescaled image. So the numbers have been changed. So every pixel we have multiplied by 2. So instead of 2, suppose if you want it to be, if you change it to 1, then it remains the same image. Here you can see the same. So this way you can rescale your image to any other values for maybe for better visualization. Actually now when I was rescaled to 5, it is not visible clearly. So the pixel intensity is just saturated. Like this was the most simplest image, like image rescaling. Now let us see some geometric transformation on the images. Suppose now if we want to rotate the image by certain angle. Actually OpenCV has even in GDAS geo transformation, like with every image we were storing geo transformation information also, like the angle, whether if the north is up, that angle will be 0. Otherwise, that in geo transformation also we were storing that information like angle. So instead of that, actually OpenCV, suppose if you want, instead of rotating the entire image, you can even rotate certain portion of our image also. Actually in OpenCV rotation matrix is stored in this way. So now let us see that how do we rotate an image using OpenCV. So OpenCV, actually first we have to import the OpenCV package. Actually it is by name, package name is CV2. So import CV2, and anyway numpy array we are. Now instead of taking the 3-band image, we will just now take the 1 band from the image. So now suppose I am just taking the band 0 of the image. So image 0 will contain the pixel intensities in band 0. So now if I see img 0, so this will be just 2-dimensional array. img 0 is actually 1-dimensional array. Not img 0, I have to take this image 0, not img 0, I have to see the complete image. So this is actually now from my 4-band image, I have just taken the first band. So we will just take the first band, for example, like we are working on the grayscale image. So anyway, first we are getting the rows and columns. So there is a function in OpenCV library like cv2.get rotation matrix for 2D. So get rotation matrix for 2D. So there we need to pass these rows by 2, columns by 2, and by how much degree you want to rotate. So the second argument is by how much degrees you want to rotate. So 90 degrees suppose if you want. So then it will return us a rotation matrix. Now if you inspect, this is the rotation matrix for this 90-degree rotation. Now after we got the rotation matrix, then we can apply this rotation matrix to the CV2. So that will be like CV2.warp affine. Then there we need to ask like which matrix, like your image data. So IMG contains our image data, then the rotation matrix, then columns and rows, like how many columns and rows. Suppose if you want to rotate the entire image, then total rows and columns. So this way it will create a rotated image. Now let us visualize. So this was our original image and DST was our rotated image. So here you can see that the image got rotated by 90 degree. Now suppose if you want to change it, change it to 180. So now you can see that the image got rotated by, it just got flipped 180 degrees. So that way you can rotate your image to any angle. Now let us see, suppose your image is noisy and you want to smoothen your image, like suppose you want to blur the edges in your image or want to remove some noise from your image. So one of the basic technique for smoothening the image is applying a convolution filter on your image. So what is convolution filter means? Convolution filter means suppose you will select a window, like you will select a 3x3, 2x 3x3, 5x5 or one matrix. So every pixel's value. Now suppose you have taken here we can say that we have taken a 5x5 kernel. So this 5x5 kernel we will impose over an image, and intensity of every pixel will be calculated by averaging, because these all coefficients are 1. So this 1 this kernel will be imposed on the every pixel of the image, and this value 1, this will be multiplied by the pixel intensity coming under that pixel, and that will be divided by 25. So this will be like average of all 25 neighboring pixels. So every pixel's intensity will be calculated as by taking the average of all neighboring 25 pixels intensity. So with this way we can smoothen our image, or this is called a convolution filter. So like then this particular kernel will be sliding over our image one by one. So initially you will take first 5x5. So there the center pixels intensity will be calculated as the sum. So if this one will be computed, so we will multiply every pixel intensity with whatever number is available here. So after that, then we are dividing it by, because this is 5x5 25. So what will happen here? Every pixel intensity will be calculated, will be the average of all 25 surrounding pixels. So this way we can smoothen our image. Now suppose similar way you can change the size of kernel. So by changing the size of kernel, your smoothing will change. So instead of 5x5 you can change 3x3, 7x7, or you can increase 9x9. Suppose if you want to average over more area. So generally, actually, this pixel dimension is taken as an odd number, because if you take it as, it becomes symmetric. Otherwise, if it is even number, it becomes asymmetric. So generally, the kernel size is taken in an odd number. So for that, suppose now we will create a kernel so of 5 by 5. So there is a function explained in NumPy lecture, np dot once. So we want to create np dot a 2D matrix of 5 by 5 size, and we are just, instead of 125 1 by 25, we are multiplying it by, dividing it by 25. Now if you see the kernel, if I don't divide it, so this is 1 by 1, because now we want to divide it by 25, so that kernel, you will see this becomes. Now for this, now suppose now this particular kernel, this filter you want to apply to your image. So there is a function cv.filter2d, cv.filter2d convolution. Then here you have to pass your first argument as your image. So on which image you want to apply to the convolution filtering. So image and -1, actually this is the depth. Depth means the data type used in your image. So if you are passing it -1, the destination image data type also will be the whatever you have used. So if you know your original image data type is integer, in the convolved image or filtered image, convolved convolution filtered image, the data type of pixel intensity will be the same as in your source image. And third argument is the kernel, which type of kernel you want to apply on your image. So then this will, now let us see the visualized image. So here, so you can see slight differences in the convolutionally filtered image. So instead of 5 by 5 kernel, suppose if you want to apply a 3 by 3 kernel, you want to make your window smaller, you can pass 3 by 3, and you can pass it here 9. So this way you can apply any convolution filter to your image. Next, suppose if you want to blur your image, like you want to remove some noise or remove the edges, like actually removing the high frequency contents from your image. So there are actually multiple types you can use, like there are different filters for removing the blur. One is simple blur, then actually the kernel you can create based on the Gaussian, or like median blur, like median will be median of all the 5 images, all whatever kernel you take, since that will be the, like here we are just adding. So there, like instead of adding in the median blur, median convolution filter, the median of all these pixels will be taken as the new value for this particular pixel. So similar way Gaussian distribution and so on. So like suppose if you want to use simple average, you can use blur, and you have to specify the size of your kernel. Then suppose if you instead of, then you want to use a Gaussian blurring, Gaussian filter. Then suppose if you want to calculate, take the median of that images, then there is a median function. So this will, now suppose we visualize these 3 differences. So here you can see that this was our original image, then these are the images after applying different convolution filters to our image for blurring. Anyway, we are not able to make out clear differences between two images because all are looking similar. So similarly, next operation is morphological transformation on image. Morphological transformation, or that is called like neighborhood operation. So morphological transformation are the some simple operation based on the shape of image. So generally we perform the morphological transformation on binary images. If we need 2 inputs, so it needs 2 inputs. One is our original anyway. Second one is called the structuring element, or second is the kernel. Like which kernel? Suppose you want to calculate the value of your pixel based, like this is like we want to calculate the value of the particular pixel based on how many neighboring pixels. So that, like, or the shape of the, like which shape of pixel. So that is called the kernel. So this kernel will decide the nature of operations. Because there are basically two basic morphological operations. One is called erosion, other is a dilation. So let us see that how do we apply erosion and dilation on our images. So what is erosion? So the erosion is just like soil erosion. So it erodes away the boundaries of foreground object. So wherever there are, like, there is a clear distinction between the background and foreground. So what it will do, it will just erode away the distinction between foreground and background. So how does it do it? The kernel slides over the entire image like a 2D convolution image. So a pixel in the original image, whether either 1 or 0, will be considered 1 only if all the pixels under the kernel is 1. Otherwise it will be eroded. So you take an example of, suppose if you take the kernel of this shape. So this particular kernel will be imposed on the original image, and the in the original image the pixel value will remain 1, will be 1 only if all the neighboring pixels, if all the pixels in these locations are 1, then only the pixel in resultant image will be 1, otherwise it will be 0. So if all the neighboring pixels have the value 1, then only that pixel will be 1, otherwise the pixel will change to 0. So this way we will contract the boundaries of our edges or foreground object. So let us see that how do we create. So now suppose again we are creating a kernel of 1 by 1. So all are 1. Then suppose if you want for eroding the image, for applying the eroding operation, cv2 dot erode, then you have to pass the image on which you want to apply the erosion operation, then kernel and iterations, like how many times you want to repeat the operation. So if you are passing it as 1, so our IMG is our original image and erosion is our eroded image. So here you can see the difference between images. So here a brighter portion is more. Then similar way there is another operation called dilation. So dilation is just opposite of erosion. Here a pixel element is 1 if at least one pixel under the kernel is 1. So if at least any one of the pixel under that kernel, if it is 1, then the output pixel will be 1, otherwise it will be 0. But in case of erosion it was all pixels must be 1, then only the output pixel will be 1. But in case of dilation, if any of the pixel under the kernel is 1, output will be 1. So like in cv2.erode, there is a function called cv2.dilate. Then it takes the same arguments, original image, then which kernel you want to apply, and how many iterations you want to go through. So this is the original image and this is the dilated image. So here you can see the difference between these two images for this area. Next is edge detection. Now suppose how do we do edge detection in our image? So Canny edge, for that in OpenCV there is a directly Canny edge detection algorithm. Actually Canny edge detection is a popular edge detection algorithm. It was developed by John F. Canny in 1986, and we will not discuss how it detects the edges. We just use it for edge detection. So actually for this, first the requirement is for this the image data type should be 8-bit integer. So we have an image already, so we are just converting it to the 8-bit integers with this function. And next we have there is a function called cv2.canny. cv2.canny, then it takes 3 arguments. First is your image, and second is lower threshold and upper threshold. So here you can see that this was our threshold. If I change, So here you can see the difference between the images. So this way we can, with Canny Edge, we can so some edges we can extract from our image. So once this is done, then so this is the basic introduction. So you can explore more about the image processing using. Oh, so you can read the OpenCV tutorial. There are a lot more functionalities available. So this was just basic introduction to the image processing. So this way you can do any kind of image processing. So there is one more package like scikit image or 7 scikit image also you can use for like a contrast enhancing, histogram equalization, and so on for better image visualization. Or you can apply many image processing to like image registration and other things you can do with OpenCV or scikit image. So next topic today is image classification. So here this was the basic image processing. Now next is image classification. So what is image classification? So image classification is assigning pixels in the image to categories or classes of interest. So in our image we will have multiple pixels. Now assigning that every pixel to the assigning every pixels in the image to categories or classes of interest is image classification. So it is, you can think it like as a mapping from the numbers, like our original image will have pixel intensity, like maybe pixel intensity red, green and blue pixels. So it is a mapping from assigning these numbers to symbols, like this pixel is built up pixel, or this pixel may be water body pixel, or this is a vegetation, this is a bare soil, or so and so on. So image classification is just mapping from those raw DN values to some different classes, like this pixel is vegetation, this is water pixel, this is built up area and so on. So that is called classification. So like here you can say that, see that this was our original 4-band image, and then we have assigned every pixel to some class. So like this pixel is a water pixel, and this pixel may be the color in green, that may be vegetation, this is built up area and so on. So that is this is classification. So in order to classify a set of data into different classes or categories, the relationship between the data and the classes into which we are classifying them must be well understood. So if we are able to understand the relationship between the classes and the pixel values, then only we can correctly classify the image. So computer classification on remote sensed image involve the process of the computer program learning the relationship. So we so this is learning. So by the learning we will associate these two things together, like classes and pixel values. So computer classification of remotely sensed images involve the process of computer program learning the relationship between the data and the information classes. So that is called learning. So learning the mapping between pixel values and classes. So actually there are two types of learning. One is supervised learning and another is unsupervised learning. So learning process is supervised learning process is designed to form a mapping from one set of variables to the another set of variables. Like one set of variables is our data. So in data means the pixel intensities may be in different bands, and mapping that that intensities in different bands to a set of variables, maybe like classes. Like suppose if you want to classify our image in 4 classes: water, built up and vegetation. So that is supervised learning. So in case of supervised learning, there will be a teacher or training data involved. In case of unsupervised learning, we need to explore the data space and discover the pattern or data distribution. So like here we can see that there are two types of learnings. One we call supervised classification and another we call unsupervised classification. In case of supervised classification, we will have a teacher or what we call training data. So in the training data, we will that is all the domain knowledge. Like here we can see that if a pixel is of class A or water, it will have certain properties. If it is a pixel of type B, it will have some other properties. C has other properties. So here like we have a training data. available. So with supervised classification, it will try to associate all the pixels with these training data, and based on this, it will try to predict or classify our new image. But what happens in case of unsupervised approach? Unsupervised approach, what it will do, it will try to statistically relate all these pixel values and then cluster them based on their based on their spectral matching. So later on, suppose if you suppose these were numbers, so these all 98 numbers may have been fitted to class B, C, D, A, like in different classes. Then finally, the user has to interpret like these all classes belong to water. Then B are agriculture, C may be rock, and so on. So in case of supervised learning, already we have some training data, and we will try to relate our new data to this training data. But in case of unsupervised learning, so statistical similarity between the data, we will cluster the data, cluster the pixels based on their statistical closeness. So later on, the person who is using the data, he has to relate like these all A belong to some particular class, B belongs to particular class, or C belongs to some other class. So this is called unsupervised classification. So what are the features in an image? Actually, we will classify the image based on the features. Features are the attributes of the data elements based on which the elements are assigned to different classes. So like maybe these features, like feature maybe like suppose if you are classifying the image based on pixel intensity in one band. So this is we are just classifying the image based on just one feature. Similarly, suppose we have a multi-band image. Now suppose we have three-band image, then the image has three features like pixel intensity is red band, green band, and blue band. Now this our pixel has three features. Now suppose it can have more number of features. So features may be the measurements made by the sensor in different wavelengths of EM spectrum, maybe visible, infrared, or microwave. So these are features. So we will classify the images based on these features. So this was our learning. Now supervised classification anyway. In the case of supervised classification, we have the advantage of an analysis or domain knowledge using which the classifier can be guided to learn the relationship between data and the classes. So in case of supervised classification, we will have a training data available. So and the training data, and based on that training data, we will the model will guide the classifier to classify the images. In the unsupervised classification, the access to the domain knowledge will not be available. The data will be analyzed by numerical exploration, where the data will be grouped into subset of clusters based on their statistical similarity. So later on, when the data is fragmented into the data is arranged into the cluster, then we have to interpret the cluster like this cluster belongs to the water, this cluster belongs to built up, and so on. So we'll now, this is the basics of this is basic theory. Now let's do some practical analysis. For practical classification, we will use a package Python library called scikit-learn. So scikit-learn is one of the most popular libraries for machine learning in Python. So we will start with unsupervised classification. In case of unsupervised classification, we don't have any training data. So we will cluster the data based on, we will cluster the pixels based on their statistical similarity. So all the pixels it may be like all the pixels which have similar pixel intensity, they will be like all water pixels generally will have same reflectance. So based on their, we will cluster the pixels on their statistical similarity. So first algorithm we will use for classification is k-means clustering algorithm. So suppose how do we do k-means clustering algorithm is one of the basic algorithms for unsupervised classification. So how the k-means clustering algorithm works? So what happens, we start with, we randomly choose, suppose now we have an image. Now suppose we want to classify the image into 4 different classes or 5 different classes. So what the algorithm starts with, the algorithm first randomly chooses k examples as initial centroids. Suppose now we want to break into k classes. Then first randomly the algorithm randomly chooses k initial samples as initial centroid. Suppose this was our original example. Then what? Then while the condition is true, first it creates k cluster by assigning each example to the closest centroid. So initially suppose this was our original data. So what it does, first it randomly chooses four clusters, four centroid, it chooses four centroids. Then it will determine that this pixel belongs to which. So, based on its nearness to the centroid of the pixel, it will assign this pixel to some that particular centroid. Then what happens that once this in the second iteration, then it will compute k new centroid by averaging the examples in each cluster. Then it keep on repeating the process until there is no change in the clusters. So for example, suppose these are our pixel intensities in red band. Suppose these were our pixels, like first pixel has intensity 3, second pixel this was our original intensity. Now initially suppose if you want to break it into four, cluster it into four classes. So initially what will happen, we will choose four random. So it has chosen four random centroids. Now based on the closeness of this pixel, so the pixel will be assigned to this particular centroid. So here you can see that now we have chosen four centroid. So these all the pixels have been assigned to this centroid. So these pixels are part of this, because these pixels are closer to this centroid. So these pixels have been assigned to this class. Then suppose then these pixels are assigned to this class, and these pixels are assigned to this and to this. So in the first pass, now what will happen in the second pass? Now the centroid will be calculated based on now in this class there are four pixels. So we will calculate the average of these four pixels, and the centroid will be shifted to the center of these pixels. Then similar way, the average of these pixel distances, then we will accordingly will shift the centroid. Then this pixel will be centroid to this pixel also may be shifted to this. Then we will assign the next, again we will reassign the pixels to different clusters. Like maybe for example here you can take, now the centroid of the pixel has shifted here, and these four pixels have come to this, and now here the centroid has shifted to this place and this. So this way this process continues until there is no change in these centroid values. So suppose this is an example, last it might convert somewhere like this. So this way now we have clustered the pixels into four classes. So that is k-means clustering. So let us see how do we do it in with program. So anyway, so k-means clustering is the most simplest approach. So initially what we will have, we will choose, like suppose if you already know, so k clustering works best when you know already that these many clusters may be available in your data. So suppose you choose the number of clusters. So initially you select the k random centroids. Now you calculate every pixel, like now you classify the pixels according to based on their distance, like based on their distance, the nearest, based on distance to the nearest centroid. Like these pixels are near to this centroid, so these will go to this class. These pixels are near to this, these will go to this will go to this. Then in the next iteration, now you have to calculate the average of all these pixels. So wherever the average comes, we will shift the centroid to that point, and again reassign the pixel to different clusters. We keep on repeating this process until there is no change in the centroid. So once there is no change, then the model has converged. So then we can classify the pixels. So now here we have a multiband image.tiff. Anyways, this similar way I am opening the image for reading. Then I am reading the data. So initially first we will do the clustering. Suppose we want to cluster on the single red band data. So now we are clustering the image based on the single feature. Like the single feature is pixel intensity in the band 1. So for doing this, we are importing a package k-means from the sklearn.cluster. So from sklearn.cluster we are importing k-means. Now I am extracting the red band data. So in data array data for data 1 is the red band data. So here I have extracted the pixel intensity is red band. So if I see this is a two-dimensional array. Now we want to cluster these. Suppose now we want to classify this particular image in 5 different classes. So for that we have imported k-means. So now we will create a k-means object. So k-means equal to k-means and the number of clusters you want, how many clusters you want to make from this particular data. Suppose if you want to classify the image into 5 different classes. So 5 number of cluster equal to 5, then random state. So this is the random state where you want to your cluster to start. So random state equal to 0. Once this k-means object is created, then on this we need to first call the fit method. So fit method on the data we call it a fit method. So cluster dot fit, and actually it takes a one-dimensional data. Actually it takes, like, suppose if you have 1000, because we are classifying it based on a single feature. So we are just reshaping, converting the data to a one-dimensional or a vector data, column vector. So data dot reshape, we are making it a column vector. So if you just run it, so it will classify or cluster these, like this pixel this will classify these pixels into different clusters. Now suppose if you want to extract like which pixels has been assigned which class out of 5 classes, that you can access using on this k-means object, k-means dot labels underscore. So k-means dot labels will give you the class to to which that particular pixel has been assigned. So like this particular pixel has gone to class 2, next pixel also has gone to class 2, third pixel has gone to class 0. So we have 5 classes 0 to 4, and this k-means dot labels gives the class of every pixel. Now actually this has returned a one-dimensional array. Now we have, for making it an image, now we have to rearrange this, reshape it into like whatever our original data. Our original data has the shape 1151 cross 1151. So now I am just reshaping the data to kernel dot labels to red data dot shape. Red data was having shape 1151 cross 1151. So actually this 1151 cross 1151 it has given as a one dimensional. Just for visualization I am converting back it to 2D array. Once you convert it, then let's see the plot. So here you can see that this is a classified image. So it has 0, 1, 2, 3, 4, this 4. So all pixels, so our original image was like this, and now these pixel intensities have been classified into the 4 different clusters. So this may not be very accurate or good clustering, but this is the basic introduction to this. Like this, all these belong to the same class. These pixels has been grouped into different clusters. Now this is up to the interpreter. Now we have to assign these classes. Like these is the water pixels, these may be vegetation, these may be built up, and so on. Suppose instead of this, if you want to classify it into 10 classes, you can just classify at 10. So here you can see that we have classified the image into, so it looks like a noise. So 10 classes are too big. So suppose if you want to classify it into just 4 classes, and we can change it to 4. And so here we have classified the image based just on a single feature like pixel intensity in a red band. Now instead of this, suppose if you want to classify this particular image into all 4 features, like we have pixel intensities in red, green, blue, red, green, NIR and SWIR band. Now suppose you like, let us see that how do we classify the image on the multiple features. So similar way, now we are, anyway we have a 4 band data. So I am just rearranging, reshaping the data, feature data. So now if I see the feature data, so this is my image. So this is like pixel 1's intensity in band 1, band 2, band 3, band 4. Now this I have just rearranged the data and put it into like this. This is the pixel 1 4 features. So pixel 1 has 4 features. This is the intensity in band 1, intensity in band 2, intensity in band 3, intensity in band 4. Similar way, next pixel has, these are the features of the next pixel, and so on. Now we will classify the image based on the values of based on the values of pixel intensity in 4 different bands. Here we have created a feature data. Now say same function. Suppose now if you want to classify it into 4 clusters, but now we are classifying it based on the values in multiple bands. So k means cluster, and then similar way we are calling the fit method. Fit method will classify the data, and finally we can access the labels using k-means.labels. So here you can see that now we have classified this particular image, and see this is the difference between these two. These are here, all the these pixels were coming here, and here a little bit changed. So at least these patterns are coming to the similar class. So this way we can classify the image using k-means clustering based on either single feature or multiple features. So this was the basic unsupervised. This is the one of the basic unsupervised clustering technique for image data. Next we will learn that unsupervised classification. So in the supervised classifications also, the most basic example is like is using, we can use distance matrix for classification. So that is the simplest approach, is probably the nearest neighbor. So we want to, so I will calculate the distance, like we will calculate the distance matching to the nearest neighbor. So in the case of nearest neighbor, what we will do? So we will, suppose we have some label data, find the nearest example in the training data. So in case of supervised classification, we will have some training data. We will have some training data. In the training data, we will have like we will have the pixel intensity, and these pixel intensities, if the pixel intensities are this, and the label corresponding to that pixel intensity. So in what is the basic algorithm? Like first is the nearest neighbors algorithm. So when predicting the label for a new example, we will first find the nearest example in the training data. So we will find the example which is nearest to the pixel we are examining to in the training data. Then we will predict the label, and we will take the label of that particular pixel and assign to the our new pixel. For example, here you can say that if this particular pixel is matching to the pixel x in our training data, this is nearest to this x data. So the whatever class is assigned to this x pixel in our training data, same class we will assign to this particular pixel. So similar to k-means algorithm, there is a k-nearest neighbors algorithm for supervised classification. This is also similar. Instead of examining a single label, we will examine the distance from k-nearest neighbors. So let us take an example that how do we do it in Python. So here what I have done here, I have a training data available to me. So actually what I have manually taken an image, and what I have done, I know that this particular image is, so I will see that this is my pixel. Image doesn't exist. So first thing, we have created a training data. So what I have done, suppose now we want to do a supervised classification. So what I have done initially, I have created some training data. Training data, like I have taken this particular image. So for example, I have taken this image. So in this image, I know that this pixel belongs to the, or this I take, so it is more visible. First I have created for supervised classification, as I explained, we need some training data. So what I have done in training data, I have suppose I have taken this particular pixel. I know that this particular pixel at this lat and long, this particular pixel, this pixel belongs to water class. So what I have done, I have taken this pixel and taken the intensity of this pixels in all the four bands. Similar way, suppose I have taken 3 or 4 samples from this image for the water pixels. I have taken this water pixel, this water pixel, this water pixels, and taken down the intensities of this water pixel in all the four bands. Similar way, then I have taken like for vegetation pixels, I have taken some vegetation pixels and taken down their pixel intensities in all four bands. Then I have taken some urban pixels like built up area pixels and taken their pixel intensities and assigned them to a class. So this way I have created some training data. So that, let us see this. So like here you can say that, so if pixel intensity is band like for pixel number 1, what or this pixel may be some different number. So first class, if band to band, if, this pixel's intensity, like this pixel has class 0. So if intensity is 100, 65, 56, 16 and 69, so this pixel belongs to class 0. Class 0 is water pixel, or pixel intensity is this range, these values, then also this pixel belongs to this class 0. Then pixel this. So this way what I have done, I have created some training data. If the pixel intensities are in this, are these values, then this pixel can be classified to class 0. If this pixel intensities are in these ranges, if the pixel intensities are these, then this pixel belongs to class 1. If pixel intensities are in have these values, then means the pixel belongs to this class. So in the classification, what we will do now, we will take the new image, and new image we will see that the pixel intensity is matching closely with which of these values. So according to that, we will assign the pixel that particular class. If the pixel values in our new image are matching, are closest to these values, then the classifier will assign class 0 to that pixel. If the pixel intensity matching are closest to these values, then the pixels will be assigned to the class 1, and so on. So this is our training data. So our training data, what in our training data, we have taken some random samples for all different classes and taken down their intensities in all the four bands. So this is our training data. So first we will train our model on this data, and based on that we will predict the values for new pixel intensities. Now for this, now we are just converting this to a NumPy array. Now if you see that this has 14, so we have 14 samples and every sample has 4 features. So 4 features means pixel intensity in 4 different bands. So we are taking in consideration 4 features of every feature. So similar way, we have another column called label. So label is these pixels have this label. So if the pixel intensity is have these values in band 2, it has 100, band 3 65, band 4 56, band 5 19, then this pixel belongs to class 1. So this is the label of this training data. So label will call df, we have taken the class column and dot to NumPy. So our labels, so these are the pixels of this label. So these are the intensities and these are the labels corresponding to that intensity. Now suppose if you want to do a nearest neighbor based classification. So in the scikit-learn, there is a function scikit-learn.neighbors, then we are importing nearest neighbors from that. Then next we need to create nearest neighbors object. So near to nearest neighbor, then based on how many neighbors you want to classify your new pixels value. So suppose if you want to be to be based on the one neighbor, then we can just pass neighbors equal to 1. Now our next task is to, we have to first fit, call the fit. So fit we will call out on our training data. So first we will call on this neighbor object fit method, neighbor dot fit. So this will fit the data, or this is called training. So now with this it will learn, and now suppose if you want to classify your new image. So now what we will call classify neighbor neighbor dot neighbors. So dot neighbors will calculate the neighbor of these feature data. So feature data our was this. This was our feature data. So this returns the class of every pixel. So now again we are just reshaping the to our original image, and let us see that. Now here you can see that this is a supervised classification based on the, we have some training data, on based on that training data we have classified the image using k nearest neighbor algorithm. So similar to k nearest neighbor, there is another algorithm for supervised classification that is called decision tree classifier. So decision tree classifier is a knowledge based classifier. So it is a, so DT are hierarchical rule based approaches. So it uses hierarchical rule based approach. So it predicts the class membership by recursively partitioning the dataset into homogeneous subsets, and predicts the class membership recursively by partitioning data into homogeneous subsets. So suppose this is, for example, this will be the example. So this will be a hierarchical rule based. Suppose we have some training data, and it will fit on the, like this from this the training data it will try to derive these rules. So from the training data it will learn these rules, and once it has learned these rules, then it will try to predict the value of a new pixel what it sees. It will apply these rules to the new pixel and classify it accordingly. Like for example, it takes, suppose first it will try to fit, or it will learn these rules from the training data. So suppose let us see that how it has learned. So it will take first the input pixel reflectance. Suppose it creates the rules like this: if pixel reflectance in near infrared band is greater than 50%. If it is true, then it will check if the reflectance is red band is less than 12%. If reflectance is NIR is greater than 50, and in red is less than 20%, then it says that it is a vegetation band. So suppose it derived this rule from the training data. Similar way, it derived a second rule, like if pixel reflectance in NIR is greater than 50%, it is less than 50%, and in NIR if it is less than 5%, and in red it is less than 10, then it is a water pixel. Similar way, from the training data it will derive these rules. So like here we have given these training data. So from this training data it will derive the rules, like okay, input reflection in NIR is less than 50% and less than 12, and then this pixel belongs to vegetation, and if satisfy these criteria, it is falling to the water band. So this way first it will derive the rules, and then once it has learned these parameters from the training data, so the model can be used for predicting classes for the new pixels. So how do we create? So there first we need to import the decision tree classifier. So CLF we are calling tree.decision tree classifier. So first we need to import it. So once we created a decision tree classifier, so first thing we need to fit. So a decision classifier is a supervised learning, so it takes two arguments. Our unsupervised or K means was taking a single data here, data, and corresponding to that data, what is the label. So that if the pixel intensities are this value, then what is the label corresponding to that. So this we have trained it here. So this data and labels. Now suppose if you want to predict for the feature data, so then we call predict method, clf dot predict. Now when we are reshaping it, and suppose if we see the plot here, now we have just classified into the three classes. So here like all these blue are this classification is not very good because our training data is not perfect. So suppose if you want to create better classifications, you need better training data, because I have taken few samples only. So but to some extent it has, like at least water it could classify to some extent, and green area to some extent. So suppose if you want to create a better classifier, so you need to first create better training data. So similar to this is decision tree classifier. So there is another classifier called random forest classifier. So a random forest classifier is an ensemble method which combines predictions from several base estimators built with a given learning algorithm in order to improve generalization. So a random forest is a classifier that fits a number of decision tree classifiers on various subsamples. Suppose we have a training sample data. So what random forest it will do, it will break the data into various subsets of the data, and fit those and apply decision tree on these all different subsets, and it will combine or average the outputs from those all different decision trees, and like take average from all those things. So in the random forest classifier, that fits a number of decision tree classifiers on various subsamples. So it will fit different decision tree classifiers on different subsamples and subsamples of data set, and use average of those all decision tree classifiers to classify the image for better accuracy and control over overfitting. So let's see how do we use a random forest classifier. For using random forest classifier from sklearn.ensemble, first we need to call random forest classifier, and the thing is similar. Like for random forest classifier takes another argument called maximum depth. Like this is the depth of that particular tree. This level depth 1, 2. So maximum depth is 3. So similar way we can define the map, like to which level you want to make the what depth of your decision tree. So suppose if you want to make it depth, so you created a random forest classifier, then depth equal to 20. Then the same thing is that first we need to fit the model. Fit means to data and label. So based on this data and label, it will derive the rules, and once the rules are done, then we can classify the data. So we'll call random forest data, then predict, clf.predict. We are predicting on the feature data, whatever we are original image. So once this is done, so it will return the label of every pixel. So then anyway we are reshaping it to the size of our image and plot. So this way we can classify the image using random forest classifier. So random forest classifier is an ensemble classifier. So what it does, it breaks the subset of training. First it breaks the subset of it fits the subsets of training data to different decision tree classifiers, and then finally average or some other algorithm it applies, and ensembles, like takes output of all combines all these different decision trees to make a final model for prediction. So this way we can with scikit-learn very easily we can classify or apply machine learning approaches for classifying our images. So that's all for today. Thank you very much.